Hey everyone, Kinetic Mind 89 here again. I'm going to do a part 2 to this video on magnetic force on a current carrying conductor. And I'm doing a second video because I felt a little rushed in doing the problem on the first video. And I know this kind of essentially the best parts, knowing how to work with problems after, because that's what you're getting graded on. You're not just being asked what is current. You're not being asked what the equation is. So I'm going to rework this example out of the book, and I'm doing an example out of the book to make sure I don't get it wrong, so I'll know you guys get the right stuff, the right information. I'm going to rework this example. First I'll explain it to you guys, and then I will work the problem. So essentially what we have, this here is a semicircle. It's a conductor, it's a wire. It's not a great semicircle, but I'm not a great artist. Anyways, the V is the magnetic field. It's going in the upward direction. Our I is our current on the wire. This is referring to our current on the wire. And it's going counterclockwise around the semicircle. So what we're asked for is two things, or are two things. We're asked for the magnitude of the magnetic force. We're asked for FB. We're asked for the magnitude. We're not asked for direction because that's a vector. We don't need vectors here. We're asked for the magnitude on the straight portion. So I'm just going to write straight and then question mark. Then we're asked for the magnitude FB. Again, no vector. See, this would be if we need a direction. We don't need directions. We don't need that. We're asked for the magnitude on the curve section. So I'm going to write curve. So we want to know how much force is from the magnetic field, which will be in newtons again. Force is in newtons. How much force are we going to have acting on these portions of the wire? Okay, so to get started with our first part of the problem, which is wanting to know the force on this first part of the wire. And actually, let me give you guys a little bit more information. To know the force on the first part of the wire, the only thing we really need to know is that L, the length of the first wire, equals 2R. Because remember, radius, just by definition, is the distance from the center of the circle to the outside of the circle. Any given point from the center to the outside of the circle. So that's our half of the circle here is 1R. So if you go and multiply that times 2R, well, what do you know? We have the length of this wire, and this is what we're trying to figure out. So the length of this wire is 2R. So our equation, and over here we have vector form, but we just need magnitude. We're not worried about direction, so we don't need these vector things for this problem. Later we do, but not for this problem. So FB equals ILB. Okay, well, ILB, let's plug that in. And we only have one thing to plug in, so this is our L up here. We just plug that in. Pretty simple, just some algebraic substitution here. So the magnetic force on this portion of wire is actually just 2R IB. Okay, so I did say that the answer was in newtons, but sometimes you'll just be left with problems in variable form. You want to actually have numbers to plug in. This is a case like that. We just have variable form, so this would be the final answer. Do not be shocked if you sometimes have problems that are left in variable form. I'm sure you've experienced that in a lot of your algebra. Okay, so that is the force on the straight portion. So now we're going to look for the force, the magnetic force, the force of the magnetic field on the curved portion. So to do that, that's a little bit more complicated. So for that, we're going to need to know, so we already have I, and that's going to be, now we're going back to this equation. I marked through this when I shouldn't have, because now we're using this equation. Now we need the vectors. We need the vector signs. Okay, so now our equation simply is FB equals I times cross product, two vectors, together as a cross product. Remember the right hand rule for figuring out direction. That's primarily what we need. So the cross product of these is this. Cross product of these is IB sine theta ds. And I explained this before briefly, but I'll explain this again. I don't know what part of the other video I'm going to cut off. When you have a curved section like this, or let's even do it like this. When you have a curved section of wire like this, you need to have straight sections for these equations to work. So since we don't have straight sections, we have to use some calculus, some integrals, which I'll assume you know some calculus if you're in physics taking these topics. If not, drop me a comment. I'll do some calculus videos, try to teach you guys calculus. This here is a little length. This actually, let me just, this here is a little length of wire that's straight. And say we have a DS here, and one here, and one here. And eventually, if we have all these little small pieces, all these little small DS's, we can add them up. If we know the force on each individual little piece, we can add them up. And we can know the force on the total bit of curved wire. But we can't do it on the curved wire all at once. We have to add up the little pieces. But luckily, that's what calculus is for. That's what our integration is for. So we know the cross product, and it's sine theta ds. And sine is opposite over hypotenuse. If you were to make a triangle and you were to extend, if you were to mark ds here, if you were to mark your little section, and you made a triangle and you did this cross product, that's what your answer would be. I assume that you will be able to get to that. This inside here will be d theta. That is your angle over your small little area, over your your small little triangle that is made when you're looking at ds. Again, the small little portion that you're looking for when you have to take, when you can't have a straight wire, when you have curved wire, you have a small little portion ds. But again, with this being the cross product, ds can be substituted for d theta. So further substituting our cross product, we get this. And this just again is some substitution. And the force will equal IRB sine theta d theta. Okay. Well, with that being said, we have to, now is the time we have to integrate, now that we have this. This is our general formula, but we have to account for this for over every little section, over every little angle this forms, and over every little portion. So this is our final general formula right here. But we have to do this for every little section. So now we integrate. Now we must take an integral. And in taking this integral, I'm going to erase the picture. I hope you guys have had a good enough mental representation of that. Remember, we're looking for the magnetic force on this curved section here. We're looking for the force FB. That's what we're looking for, just to be really specific and not abstract. We're looking for the force on that curved section of wire. Okay, so being that we're looking for that force, we obtained our equation. We started off with I cross product ds times b. We integrated that. We just substituted that. And now that we've substituted that, we can plug this formula, this general formula in. And when we substituted for our small pieces, our individual little small pieces. We just plugged in what those would be in different terms. And that is, and I'll just write that again. I'll start up here and write that again. And if we're looking at our small little pieces, our fragment of a force on an individual little small piece is DFB, so this is the force on one of those small pieces I've been describing, equals IRB times sine theta d theta. Alright. And in integrating this, you get IRB, and remember that R is radius, B is magnetic field, I is current, and we integrate, and those are constants actually, and those are constants because they don't change in the problem. The current, we were given I, we were given R, the size of the wire doesn't change, the magnetic field doesn't change, and the current doesn't change. None of that changes. That's why they're pulled out. But what does change is this bit here, because we're looking at these little individual sections that I call ds, and this is ds in terms of theta. It's just in different terms. That's what I meant by substituting. So these things change. This is what we're integrating, adding up the little pieces. These things do not change. They're constants. That's why they pull it outside of the integral sign. And we are integrating sine theta d theta, and that's the same thing from above, just pulling it down, writing it explicitly. And what we'll get here is IRB, so current, radius, magnetic field, times negative cosine theta, and this is after integrating. This is the answer to this integration here. We integrated we took from 0 to pi, because half of the circle is pi, 2 pi r is the circumference of the circle. And now that we have this, we need to know the bounds, which I just stated, which is 0 to pi, which, to draw that out to be explicit, halfway around a circle is 1 pi, so we zeros here, we travel halfway around, we're at pi. So if we do that, actually, we plug in all the values there. In our integration, we have, after our integration, we will plug in both values for theta. Pi will go into theta and 0 will go into theta. So I'll erase that, hoping you guys saw that well and collected all that and took all that in. What you'll have finally is negative IRB, again constants, current, radius, and magnetic field, times cosine theta, or I'm sorry, now we plugged in pi for theta, minus cosine 0. And see, is that correct? That is correct, which really didn't even need to be written, cosine 0, like that, inside parentheses, but it did need to be written because cosine 0 is 1. I'm silly, thinking it was something else. And the answer is negative IRB, so negative current, radius b, times negative 1 minus 1, and this is cosine theta, cosine pi minus cosine 0, 1 minus 1, so IRB, current times radius times magnetic field, times 1 minus 1, and that will give us 2 IRB. A negative times a negative is positive, so negative 1 times negative 1 is, this is 1 minus 1 equals negative 2 times a negative IRB is 2 IRB. So that is the force on, and this is completely drawn different. Let me draw it just a little bit better, a little bit closer to the original. That's not better either. Oh well, I'm running out of time on this video too. Hopefully I've explained it well, taking as much time. This is B, all of these lines, the direction of the magnetic field. The first part of the problem, we found I in this direction, which was easier, with the magnitude rather. Now we found the magnitude on the curved portion, and I is still going across this curved portion. And again, just to not be vague, this is FB, magnetic force on the curved portion of the wire. Hope you've enjoyed this video. Thanks, guys.